This is a triad system. And if you take the most important example of this system, hello everyone, welcome back to PLUTUS STEM. Today we are going to discuss a very important topic of general organic chemistry, that is tautomerism. So why I am saying that this is a general organic chemistry topic, because it is a subpart of isomerism, but we will see some movement of electron, pi bond dislocation. So this thing, that's why this generally it is being studied when we are going to study the general organic chemistry. So actually this is a part of structural isomerism. Structural isomerism. It is a subclass of structural isomerism, and we have already studied all other isomerism structure such as ring chain. This thing is remaining. Functional group isomeric, metamerism, chain isomerism, and position isomerism. So these all isomerism we have studied except this tautomerism. This today we are going to study. This if this is a priority of these different isomerism, so this isomerism comes second number. The first one is ring chain isomer, and the second isomerism of this structural isomerism is tautomerism. So what is the special thing about this isomerism? So all the isomerism which we have studied in the structural, like chain, position, in this we were having two different molecules. We were having two different molecules. They were having molecule formula same and structural formula different. These two were two different molecules. But here we will see there is a single compound. There will be a single compound. Let's say this ketone. It is being interconvertible to some other compound. It is being interconvertible to some other compound. And if we see, let's say there is a hydrogen is being over here, and this hydrogen will come over here, electron, and this comes over here, and this hydrogen will be abstracted by this. 1, 2, 3. From one position to three position, the movement of this hydrogen, or you can say oscillation of this hydrogen from one position to third position, like this. Over here a double bond, and this hydrogen is moving at this position now. And if you visualize this is in over here, and ol for alcohol, enol, and this is a keto group, keto. And generally, so I will discuss some other type of isomerism also, not just keto-enol. There are some other tautomerism also exist. We will but from exam point of view, this keto-enol is very important. Keto and enol isomerism, which means one form is keto, another form is enol, and generally this form is more stable. This form is more stable as compared to, generally we will see the more stable form will be this one. So that's why we will see this will be generally, the main thing is generally. There are various exceptions are there where we will see enol form is more stable, and we will find the enol form content in a higher way. So see, now we will see the basic of this keto-enol. The basic mistake which the students do is that they confuse with this keto-enol tautomerism or the tautomerism with the resonance. So I will tell you a bit tautomerism and resonance, because here also we are seeing the movement of electron, and in the resonance also we see the movement of electron like this. So this is resonance. This one is resonance. So there is a doubt between various students, they possess that, so why we are calling it as a tautomerism and this as a resonance. So that also we are going to discuss today before going to the subclasses of this tautomerism. So this tautomerism, it is a real phenomena. This phenomena is real phenomena. This is really existing within a molecule. The molecule, once we will find out, we will see this keto form, and after that it will be converting into this enol form. But this resonance phenomena, this is a hypothetical phenomena. This is a hypothetical phenomena. This is a hypothetical phenomena in which we assume that these bonds are moving like this. That's why they are showing such type of properties. Like they are exhibiting the property between the single, this bond length is between the single bond and the double bond. To explain this property, we draw these two different aromatic structure. Actually, these two compound cannot be isolated, which means that actually this thing doesn't happen, that this thing is converting into this thing. One structure is not converting into other. So that's why this is a real phenomena. This is a hypothetical. We are assuming that it might be happening like this. So because it is real, so the compound, these can be, these different form of these tautomers can be isolated or isolable. Isolated, can be isolated, can't be isolated. These tautomeric form can be isolated, but these resonance different form, they cannot be isolated. And over here we have seen the movement of sigma bond and pi bond. Sigma bond and pi bond movement taking place. Sigma bond, pi bond movement or dislocation. But in this you will see pi to pi bond, pi and star to pi, sorry, yeah. Or pi bond to p orbital. Some lone pair are there. You can say lone pair over here, that would be more like lone pair to pi bond, or pi bond to empty p orbital. So this is the way. Here only sigma bond to pi bond movement. And one more important difference is there. There only electron movement. Sorry, hydrogen dislocation, or you can say oscillation. In this we are seeing the oscillation of hydrogen, but in the resonance we will see the oscillation of electron only. We will see the oscillation of electron only. So this is the way, this is the major difference between the tautomerism and the resonance. So those students, they are being confused with this, that why we are calling it as a resonance and why we are calling it as a tautomerism. So this is the major difference over here I have shown you. So now coming back, so what are the systems that show this tautomerism? So there are two type of system: dyad system and triad system. So firstly we are going to see the dyad system. H, C, triple bond N, where the conjugation, the movement of this hydrogen will be from 1 to 2. 1 to 2, the movement of this hydrogen will be from 1 to 2, HCN. This hydrogen will be moving from here to here. Like this. So this is the movement which is taking place over here. This is also an example of tautomerism, the dyad system, where the electron, this hydrogen oscillation is taking place, and both these two structures can be isolated, and this type of isomerism is not that much popular. The most popular isomerism, tautomerism, which is over there, is for a triad system. The most important isomerism is being shown with the triad system. So we will see over here that triad system show this type of isomerism, where the oscillation will be from 1, 2, 3. 1, 2, 3. X, Y, Z. This type of moiety is there. If this type of moiety is there, so what will happen? The movement of this from 1, 2, 3, one position to third position. We will see the movement of this hydrogen from one position to third position. These are interconvertible. Then we will write down like this. So this X, single bond Y, single bond Z, and over here hydrogen. So this hydrogen is coming over here. So it is quite obvious this bond will come at this side, like this. So this is the main thing where we will see 1, 2, 3. The movement of this hydrogen. This is a triad system. And if you take the most important example of this system, that is keto-enol. And many more systems are there like ester, and we will see many more example of this. This is like our Z. Sorry. This is our Z. This is Y. And this is X. It would be better if we write down these all with different pen. Yes. So this is Z, this is Y, and let's say this is X. And over here are hydrogen. Yes. So this hydrogen at X, from here you can see this hydrogen at X, what it will do, it will move like this. This bond is coming over here. You can see, visualize the thing, and we will get a product like this, enol. Sorry. So if you see over here now again, so this is our XZ, this is Y, and this is X. So at X we are having a double bond, and at Z we are having hydrogen. So this is the triad system, and generally we will see this type of system that is being asked in exam also, and various type we will see. Generally from this system we are going to see this keto and enol tautomerism. In exam point of view, this is very, very important concept. So now we will see how what are the some necessary, one more necessary condition. The first necessary condition was this, that I have told you the system must be like this. For a triad system, it should be like this, and over here this can be like nitrogen, oxygen, sulfur, and this can be any atom. This can be any atom, but this should be like some electronegative atom like nitrogen, oxygen, sulfur, etc. So this is a system. Now we will discuss for this triad system. We will take few examples and we will see how this ratio is being changing over here. So we will see how this ratio is being changing. Like if we are having like this. So what are the most probable over here? Now that's why I have called it. It is a subpart of you can say sorry, GOC, because now the GOC is coming to the light over here, that from where we need to show the keto-enol tautomerism, which is the best substrate which we are going to see over here. This can show the tautomerism. This can show the tautomerism, yes or no? You will see from this, both of them can show the tautomerism from here. So, but generally what we are going to do over here, we will take the hydrogen from more because here also electron withdrawing group, here also electron withdrawing group. So this hydrogen is very more probable. So we will see like this. So either from this carbon 1 or either from this carbon 2. We can draw it from any one carbon like this. And this is also a stable compound if you see, due to this some extent of hydrogen bonding is there, some conjugation is also there. Double bond, single bond, double bond, sigma bond, pi bond, sigma bond, pi bond, which means some conjugation is also being seen. So to see the stability, the thing which we are going to visualize over here is resonance, hydrogen bonding, and aromaticity. And anti-aromaticity, which means least stable. So if there is a compound, if after this tautomerization, after this keto-enol formation, it is getting into the anti-aromatization, so we can say that this compound is not going to give to that direction where we are getting an anti-aromatic compound. If we are getting an aromatic compound after this keto and enol conversion, so that will be more probable part, that this we can say that this is more stable, and we are going to get a major extent of that part only. The major yield will be like if we are going to see the percentage content, so the keto percentage and enol percentage in such type of compound. So we can say over here, because we know that ketone are more stable than enol. We know that ketone are more stable than enol. So we can see over here, this is like, but generally due to this conjugation also and due to this hydrogen bonding, here the hydrogen bonding is also there, and over here conjugation is also there, which means double bond, single bond. That's why this type of interaction which is giving rise over here. So this content is a more stable. This is a bit more stable, and we are getting a 76%. This is 76%, and the rest, this one is 24%. So this is the reason why we are seeing over here. Generally, I have told you earlier also that ketone are more stable. Generally, we will see that ketone are more stable. So more extent of this we are going to find. But some cases when we are having some aromaticity or hydrogen bonding, so they are helping this form to be stable and getting in a more yield in that part. So this part is 76% yield, and here only 24%. So they are interconvertible. So more will be toward this side equilibrium and less toward this side. So this is the way. And if we see a similar type of example, because this is also electron withdrawing hydrogen, this is more acidic. That can be taken very easily. But if we take a similar type of example, if we are going to take this type of example, then we will see this is 93%. This part is 93%, and the enolic form of this is, you can expect that how much it is going to be, because now this hydrogen, this will be invert over here OCS3. So this hydrogen, they are not that much electron withdrawing due to this conjugation. Already there is conjugation present in this compound. That's why that hydrogen are not that much acidic. So this content is 93%, and this is only 7%. This is only 7%. But generally in all the cases, we are going to see keto percentage as very high. Keto percentage is very high. So if we see some more example of this type of, like if we are having a ketone group like this, this is our compound. So what do we expect if you can say Hydrogen is present over here. This hydrogen can come over here and this will move like this. Keto-Enol Tautomerism. Here also we will see a keto-enol tautomerization can happen over here. In this case, what we are going to see, if you visualize clearly, these are like this. This is OH and a bond came over here. And this is a benzene ring came into the existence, or you can say a phenol. So the content of this type of compound is very, very high, nearly 99.8 approximately. And the content of this is going to be 0.2%. Because this is gaining the high stability due to this resonance or aromaticity. This is an aromatic compound. This is an aromatic compound, and I have told you that the condition of aromatic compound is any compound should be planar. The compound should be planar. The compound should be conjugated. Complete conjugation should be there. And they must follow the 4n plus 2 pi electron. They must show the 4n plus 2 pi electron rule. So this compound is planar, all atom are sp2 hybridized, complete conjugation is there, and they are following the 4n plus 2 pi, 4 ones are 4 plus 2, and where n is whole number. So 4 ones are 4 plus 2, 6. So there are 6 pi electron are there. So this is an aromatic compound, and due to this aromaticity, this is more stable. This is quite more stable compound we are getting over here. So this compound is getting the content of 99.8%. And generally when you are studying such type of compound, so you would have studied that alpha hydrogen is being abstracted. Alpha hydrogen abstraction is quite a necessary condition to give this keto-enol tautomerism. In the keto-enol tautomerization, we are going to see that this alpha hydrogen abstraction is quite necessary step. So, but I will tell you one more exceptional example of this. This one. The alpha hydrogen are those hydrogen which are present near to the, you can say, ketone. This must be the alpha hydrogen. But here we are going to get a alpha, beta, gamma hydrogen, this one. These hydrogen will, because they are giving us a more stable product. Again the same product over here. So this type of abstraction can also take place sometime when we are getting a more stable product like aromatic product. And sometimes if you are getting a non-aromatic product, if you are having those examples in which we are having a non-aromatic moieties, like take the example of this. If we are having such type of molecule and we expect that this hydrogen will move over here and we are going to get like this OH. This is anti-aromatic. This one is anti-aromatic, and such type of conversion doesn't take place because a molecule needs stability. It will not go to that side where that is very, very unstable. The compound that is very, very, very unstable. So yeah. So regarding this compound, if you visualize this, the last example of this, we are going to discuss this example. So now how many this conversion, enol conversion are possible over here? This one and this one. So if you see, there are 3 enolic conversion are possible, and they will give rise to a very stable product. Now again, first one will be like OH, double bond here. Second one will give rise to OH, double bond at this side, and third one will give rise to OH and double bond at this side. So we can see again our resonance compound or aromatic compound. So such compound, if we are getting this type of compound, then we are going to see this phenomena with a higher yield. So that's all for this, you can say resonance. Just we will do a quick recap of all which we have studied up in this. So in today's class, we have discussed regarding this tautomerism. In that, I have told you that this tautomerism is a subpart of structural isomerism, in which I have told you this regarding this priority. This comes second in the priority table, and after that we have discussed example, like just the general example is Keto-Enol Tautomerism, and then after that we have compared it with the resonance. What is the difference between tautomerization and the resonance? So I hope this thing is now clear, and we have discussed regarding two type of system that give this isomerization, tautomerization, that is diet system and the triad system. And after that we have already discussed regarding the content also. So why we are getting the lesser content and sometimes we are getting the higher content, that purely depend on the four factor, that is aromaticity, hydrogen bonding, resonance and aromatic character. So aromatic, which means that this phenomena will not be shown. So over here this is the 93% keto, because keto is more stable. Generally the keto content will be more stable, that I have shown you over here, but sometimes due to some reasons, if we are having some resonance is there, so these content are very highly stable. These products are being shown over here. This example, sometimes we are also getting the para hydrogen substitution also taking place, oscillation. Regarding this anti-aromatic, I have shown that these anti-aromatic compound, they don't show this type of tautomerism because of this unstable compound is coming in this picture. And the last example which I have shown you over here, these three different hydrogen, they are showing the tautomerization, and we are getting a more stable product, and that is in a very high yield. So more content will be of this part rather than this keto part. And in general, I have already told you that most of the time you are getting a ketone as a more stable moiety. But if some stability is being gained due to some resonance, conjugation, hydrogen bonding, then we are going to get a higher content of this enol form also. So this was for your like tautomerism, and now we will be discussing the next upcoming videos regarding the stereoisomerism, different type like geometrical isomerism, optical isomerism, and enantiomers, diastereomers, cis, trans, EZ, anti, strain, everything we are going to discuss from this upcoming lecture. That's all for today. Thank you.